This is part 2 of the series Quadrilaterals. Now that we've discussed interior and exterior angles, we can turn our attention to quadrilaterals, and we're going to start this discussion with parallelograms. Parallelograms are quadrilaterals with two pairs of opposite parallel sides. Now they look like boxes that have been sort of squished over and tipped to one side. These symbols are the parallel symbols. So when you see little arrowheads on the sides of the quadrilateral, that indicates that those two sides are parallel. When you see a double pair, that also indicates parallelism. You might see these with open arrowheads. Anything that resembles an arrow that's in the middle of the line segment that forms the side, that indicates parallelism. Parallelograms have many properties, and those properties are what's going to occupy our attention for the next little while here. So let's turn to the first set of properties for parallelograms. That property is stated in the parallelogram opposite sides theorem. If a quadrilateral is a parallelogram, then both pairs of opposite sides are congruent. So here you can see this congruent symbol matches with this one, so these two sides are congruent. And these two sides are congruent. These sides are not necessarily congruent to these sides. I'm going to go ahead and prove this theorem now, so that if you're not interested in seeing the proof of this theorem and where it comes from, feel free to skip ahead. For those of you who want to, let's get into the proof. I've gone ahead and written the given statement, and before we actually begin the proof, let's do a little bit of planning to see approximately where we're going to go with this proof. Now, we don't really have much information to go on in here, so I'm going to have to add some information. And the first thing I want to add is going to be a segment here between A and C to create two triangles. Because what I have here is I have two parallel lines, and if I add a diagonal in here, I can create a transversal. That will create some congruent alternate interior angles, and I can use that sides congruence properties to show that these two triangles are congruent, and then I can show that these two opposite sides are congruent. So that's a general plan for our proof. So let's go ahead and get started. The first thing, I want to draw in this auxiliary line. So let's go ahead and draw that. And we can write then, draw AC, and the reason through 2 points there is one line. To make our job a little easier here, I'm going to label these new angles we created. I'm going to call this 1, 2, 3, and 4. Now we can say, since we have two lines cut by a transversal, we know that angle 1 is congruent to angle 4 by the alternate interior angles theorem, and since AD is parallel to BC, and that's cut by transversal AC, angle 3 and angle 2 are congruent. So we can say angle 1 is congruent to angle 4, and angle 2 is congruent to angle 3, and that's alternate interior angles theorem. Now, because AC is being shared by these two triangles, we can say that AC is congruent to AC. That's the reflexive property of segment congruence. And so this guy is congruent to himself. Now, we know that this triangle is congruent to this by angle, side, angle, angle, side, angle. So triangle A, B, C is congruent to triangle C, D, A. And that's angle, side, angle, congruence. Now, we know that AB is congruent to CD, so AB is congruent to CD, and we know that AD is congruent to BC. AD is congruent to BC by CPCDC. Corresponding parts of congruent triangles are congruent. And our proof is complete. We've proved what we set out to prove. So now let's look at the next property of parallelograms. This next property is stated in the parallelogram opposite angles theorem. If a quadrilateral is a parallelogram, then both pairs of opposite angles are congruent. So here we have angle A is congruent to angle C, and angle B is congruent to angle D. So let's go ahead and prove this theorem. This theorem is going to be proven in very much a similar way to the last theorem that we proved, but we're going to have to go a little bit further. So let's get started with this. Our plan is going to be, again, to create two triangles, to prove those two triangles are congruent, and thereby showing that these two opposite angles are going to be congruent. So that's our first piece. Let's go ahead and do that. So we'll write in our auxiliary line here, and then we will state okay. Now we can do our thing that we did before. We know that because this is parallel to this, we know that this angle is congruent to this angle, and I'm going to go ahead and add these numbers 2, 3, and 4. And because this is parallel to this, these two angles are going to be congruent. So that gives us angle 1 is congruent to angle 4, and angle 2 is congruent to angle 3, and that's alternate interior angles theorem. I'm hoping at this point you're starting to see the patterns forming, because these patterns are very common in this kind of a proof. Now we can say that AC is congruent to itself, reflexive property of segment congruence. So we know this is congruent to itself, and we know the triangles are congruent. So triangle A, B, C is congruent to triangle C, D, A, and that's angle, side, angle, congruence. Now in this case, we're going to say that angle B is congruent to angle D. Angle B is congruent to angle D by CPCTC. What we have left is to show that angle BAD is congruent to angle BCD. We could repeat this entire process, draw in an auxiliary line between B and D, and show that these two triangles are congruent to each other, and therefore those two angles are congruent. Or we can use what we already know. So that's probably the easiest way out. Let's go ahead and do that. We know that this angle is congruent to this angle. Angle 1 is congruent to 4, and 2 is congruent to 3. So we can say that the measure of angle BAD is equal to the measure of angle 1 plus the measure of angle 2. So the measure of angle 1 plus the measure of angle 2 is BAD, and the measure of BCD is the measure of angle 3 plus 4. And that is the angle addition postulate. So this big angle is made of these two small ones, and this big angle is made of these two small ones. We know then that because angle 1 is equal to angle 4, I can use substitution to substitute the 4 in for the 1 and the 3 in for the 2, because angle 2 is congruent to angle 3. So I'm using substitution here to show that those two are congruent. Substitution property of equality. And then we're going to say that we have this, the measure of angle 3 plus the measure of angle 4 equals the measure of angle BCD. And so we have A equals B, B equals C, therefore A equals C. That's the transitive property. Yes, that's come back. It's never going away. These are the properties we've used throughout the entire year. We're going to have to continue to use. So it's important to keep these things in mind. So measure of angle BAD is equal to measure BCD by the transitive property of equality. And then we switch from equality to congruence by the definition of congruent angles. Now, to be puristic about this, I probably should have, inside here, I probably should have said the measure of angle 1 equals the measure of angle 4, and the measure of angle 2 equals the measure of angle 3. That would have been the most appropriate way to do this, but I just cut a corner here. And now that I'm explaining it to you, you would know that that's what you'd have to do right in this piece here. So you'd have to put that step right in there, that the measure of angle 1 equals the measure of angle 4, and the measure of angle 2 equals the measure of angle 3. Well, let's go ahead and work a couple of examples to get these ideas locked in. This example tells us in this parallelogram, let's go ahead and find the values of x and y. Well, the first piece is really easy. We know that the opposite angles are congruent, so if angle C is 65, then angle y has to be 65. So that was fairly trivial. And the opposite angles theorem says that this side is congruent to this side, so we know that x plus 4 equals 12. So x plus 4 equals 12, x equals 8. So let's go ahead and work another problem. And here we have another parallelogram, and we want to find the length of FG and the measure of angle G. Again, opposite angles are congruent, so we know that the measure of angle G equals 60 degrees, and we know that opposite sides are congruent, so FG is equal to 8. And just for kicks, let's do one more example. Here we have another parallelogram, and we have 2x for angle J and 50 for angle L. We know opposite angles are congruent, so 2x equals 50, and therefore x equals 25. We also know that these two sides are congruent, so 18 equals y plus 3. Subtract the 3, 15 equals y. Hopefully you find these relatively basic. Opposite angles in parallelograms are congruent. Opposite sides in parallelograms are congruent. And so let's move on to the next property.